If you were asked, "What is infinity?" what would be your response? A lot of people will say it is something too big to be counted. What is the biggest number you can think of? Is it 10 to 100? 10 to 1,000? Even those are still numbers and we can use them in math. I shall discuss a few problems that exist for the first part of this video, followed by solutions. Let us look at a few definitions. In math, infinity is defined as a number which is greater than all natural numbers. Do you see a problem with that definition like I do? The set of natural numbers itself is infinite. You cannot know or count all natural numbers, so how then can there be something bigger? It also says infinity is a number, but is it? Another definition goes like this. A set of numbers is infinite if there is a one-to-one correspondence between that set and a proper subset of itself. For example, the equation x plus 1 equal to x is true if and only if x is equal to infinity. This definition also treats infinity as a number, since it can be used to carry out mathematical operations such as addition. But is it a number? The dictionary defines infinity as endlessness, unlimitedness, boundlessness, absence of beginning, and or limit to size. This definition does not treat infinity as a number, but rather as an idea of something unreachable. As a result, infinity cannot be acted upon by mathematical operators, and therefore, things such as n times infinity, infinity plus 1 are meaningless. Let's suppose we agree that infinity is a number. Then, n times infinity is possible and the answer is infinity, because infinity times anything is infinity. If that is true, then 0 times infinity is also infinity. Wait a minute, but 0 times any number is 0. So this should be 0 because infinity has been considered a number, no matter how big. So, if we treat infinity as a number, we will get stuck with problems such as this one. The next option is to treat infinity as an idea, not a number, in which case no calculation can be allowed with infinity, but we need to be able to do math with it. So we still have a problem. Recall that this is the same kind of problem that arises when you are dealing with 0. That we have seen in the first video of this series, titled 0 cannot be equal to nothing. You can find it with other follow-up videos of this series under the 0 and infinity playlist of this channel. If you like the content of this video, please show your support by clicking the like button. I will be answering all the questions that I have posed, and will be solving all the problems and paradoxes that arise when dealing with 0 and infinity in an unambiguous manner. So, if you want to know how to do calculations with 0 and infinity, as simple as you do with other numbers, click subscribe and follow me on this journey. Before I give the undebatable definition of infinity, let's first of all look at why the above definitions don't cut it, and how the idea of infinity is wrongly used in science and math. I shall keep it as simple as possible for you to understand, using real applicable examples. Example 1. Let us look at the mathematical analysis of a length. The length equation is given as follows. f is the focal length of the lens, and this is unique for every lens. U is the distance between the object placed in front of the lens and the lens, and v is the distance between the image of this object that the lens will produce and the lens. When an object is placed too far from the lens, like here for example, we say that the object is at infinity. That is, u is equal to infinity. Infinity in this case simply means that u is far greater than the focal length f. Putting u equal to infinity in the equation yields 1 over f equal to 1 over v, since 1 over infinity is 0, which means that v is equal to f. So, for objects at infinity, their image is formed exactly at the focal length. Let's take a lens with focal length 1 meter and place an object 100 meters from it. 100 is far greater than 1, so this object is at infinity, and every other point from there hence. So 100 is equal to infinity for this case. If we now use a lens of focal length 0.5 meters, we only need to place that object about 50 meters away for it to be at infinity. So for this lens, 50 is equal to infinity. For a lens of focal length 0.1, 10 meters is enough to consider infinity. We can continue like that for any value of the focal length and have infinity be equal to many different values. So you see that by the way infinity is used in this concept, infinity is equal to everything. That is, every number is equal to infinity. Is that true? Of course not. But the physicists solve their lens problems and the engineers produce beautiful lenses and other optical equipment using this approach. Another problem is that if infinity is really what is said it is, and the lens equation is correct, then we should be able to see all objects at the edge of our universe using any lens. But can we? Let's look at another example. If you bring two magnets together, they experience a force. The closer they get, the stronger the force. When you move them away from each other, the force reduces until at some distance and beyond, they no longer experience that force. The equation of the force between them is given as follows. Forget about the other terms and focus on the relationship between the force and the separation r. We see that F is inversely proportional to r, and F is equal to 0 when r is equal to infinity. So let's say for our example, the magnets have to be at least 1 meter apart before they don't experience a force. So infinity is equal to 1, and hence everything. This is how infinity is used in all of science, and come to think of it, it makes sense. Let's put in some numbers so that you can see that it makes sense to treat it that way. The energy of an electron in an atom is given by a constant times the integral from r to infinity of 1 over r squared. R is the distance between the electron and the nucleus. Integrating yields this, and subbing in the limits produces the following. For a hydrogen atom, R is equal to 0.5 exponential minus 10 meters. 1 over this value of R gives 20 billion. Imagine an electron is like 1 meter away from its nucleus. 1 meter is an infinity for this situation. So let's sub that in the equation. We have 1 over 1, which is 1. So you see that subtracting 1 from 20 billion will not produce any significant change. So we can calculate the electron's energy to very high precision by treating infinity this way. Because it works for everything that we try to do, we become blinded from the implications of this. As we have seen, this means that infinity is equal to everything, and that is the problem. So how then can you expect infinity to behave normally when you define it abnormally? It is because of this kind of definition that gives infinity the properties that they have, such as when anything is added to infinity, it remains infinity, and so on. But of course, that is what you get. If you add 3 to 1 in the example of the energy of the electron, 1 over infinity becomes 1 over 4, which is 0.25, which is even smaller than the one we obtained before. So the overall result remains the same. Since 1 is infinity, then 1 plus 3 is still infinity. Hence, every other number is infinity. Even basic mathematics tells you that the definition of infinity is wrong. 1 times 1 is always equal to 1, no matter how many times you perform that operation. This clearly means that 1 to the infinity should also be equal to 1. But when you solve this problem in math, you find that the answer is 2.7, which is equal to the exponential function. In few minutes, I will present you with unequivocal solutions to all such problems. So please press that like button and the subscribe button. Let's start seeing solutions. The definition of infinity is very simple and straightforward. Infinity is defined as the multiplicative inverse of 0. Mathematically, infinity is equal to 1 over 0 uniquely. Check out my video on 0 to see how 0 is defined. 0 is not absolute, and therefore infinity is not absolute. Both must be defined for every situation you are dealing with. So you can look at infinity as a set of numbers that are too big for a particular situation, and 0 as the set of numbers that are too small for that situation. So you have to define those sets for every situation. Next, you convert the units of that situation such that the smallest value should be equal to 1 and the largest value be equal to some number, say n, such that anything less than 1 falls in the 0 set and anything after n falls in the infinity set. So there will be a one-to-one correspondence between the 0 and infinity sets, such that for every value chosen from the infinity set, there exists a number in the 0 set which is the inverse of that number in the infinity set. That is, 0 times infinity is equal to 1. So you can solve your problems using these units and then convert your results back to SI units. Let me use an example to demonstrate this. Let us go back to our lens problem. Distances are measured from the center of the lens. So, the smallest possible distance which an object can be placed from the lens is equal to the radius of the lens. And that is when the object is touching that lens. Let's assume for this lens, the distance from which we can call infinity to be 9.9 units, and the radius of the lens to be 0.1 units. Working in one decimal place, the intermediate numbers are as follows. These are the only numbers that can be considered as regular numbers for this situation. So any number below 0.1 falls in the 0 set, and any number above 9.9 falls in the infinity set. The first number in the infinity set is 10.0, but 1 over 10.0 is 0.1, which does not fall in the 0 set. That is why we need to transform this scale into another scale where there will be a one-to-one correspondence between 0 and infinity. 0.1 is therefore equal to 1, and using only whole numbers, the new scale is given as follows. So, there are 109 regular numbers for this situation. 109 corresponds to 9.9. So for this case, every number n obeys the following inequality. 0 falls on this side of the inequality, and infinity falls on this side. Now, the first number in the infinity set is 110, and 1 divided by 110 gives 0.009, which falls in the 0 set, and we therefore have our one-to-one correspondence. So for this situation, 1 over anything bigger than or equal to 110 is equal to 0. Let's use this to solve a problem. A lens of radius 0.4 units has focal length 0.6 units. If an object is placed 1.8 units away, how far from the lens will the image fall? For this scale, 0.4 is equal to 1 and 0.6 is equal to 3. Our object position is 3 times greater than our focal length. So, on our new scale, the object position should also be 3 times greater. And this gives 9, which is 3.3. So, f is equal to 3, and u is equal to 9. And we have to find v. From the length equation, subbing in these values yields 9 over 2. So this tells you that the image position is half the object position. So since our object position is 1.8, then the image position v will be 1.8 divided by 2, which gives 0.9 units. If you sub in u equal to 1.8 and f equal to 0.6 in the length equation like so, you arrive at the same result. I know moving from one scale to another just to solve a problem is tiring, but the purpose of this is not to solve problems simply, but to clarify the idea of infinity. Look, if the object was placed 10.1 units away, this will correspond to u equal to 111 on the order scale. Maintaining f equal to 3, the equation becomes 1 over v equal to 1 over 3 minus 1 over 111. 1 over 111 is equal to 0, according to our definition. So, v is equal to 3. This tells you that the image will form at the focal length, which translates to 0.6 on the Weyl scale. So infinity is not an unimaginary big number, or whatever kind of number you were taught to be. It is a relative term, just like 0. You have been told that nothing can travel faster than the speed of light c, which is 300 million meters per second. If that is true, then nothing can ever travel slower than 1 over c in terms of magnitude, which is 3.3 exponential minus 9. That is pretty close to 0, but not quite 0. And this number is a very big number when it comes to atomic scales. This means that no object in the universe can ever be stationary, and we can write v is less than c and greater than 1 over c, where v is the speed of any object in the universe. But in spite of that, we have problems solved using zero velocity. This is just to tell you that we always just approximate everything, and nothing is ever quite what it seems. Let us now look at multiplication with infinity. But before we move on, please subscribe. It only takes you 1 second and 1 click. From our previous example, infinity was any number bigger than 109, such as 110. 2 times 110, 3 times 110, and so on, will all give numbers greater than 110, which is infinity. So this means any number times infinity is infinity. As much as that idea is true, that doesn't mean that 2 times 110 is equal to 3 times 110. Otherwise, it would imply that 2 is equal to 3, and therefore equal to all natural numbers. In general, even though n times infinity is equal to infinity, m times infinity is not equal to n times infinity. The two are only equal if n is equal to m. Similarly, infinity plus n is not equal to infinity plus m. The same thing with all other mathematical operations that involve infinity. So now you see that infinity, like 0, is not an absorbing number. N times infinity is equal to n times 1 over 0. We know that 0 is equal to the magnitude of 0 plus epsilon. Subbing it here and inverting both sides yields this, which can be expanded to this. Absolute 0 represents nothing. So this term is equal to nothing, and it goes away. So we can now invert the equation again to have n times infinity equal to n over epsilon, meaning that infinity is 1 over epsilon. Let us use what we have learned so far to solve the problem 1 raised to the infinite power, which by common sense should be 1 times 1 times 1 and so on, which should be equal to 1. If you have done some advanced math, you would have noticed that the answer to 1 raised to the power of infinity is 2.7, which is equal to the exponential function. And they tell you that it is because 1 is a special number. There is nothing special about it. Let me derive the same result using what I have been showing you so far. In the last video, we saw that every number n is equal to the magnitude of n plus some uncertainty term epsilon. So if n is equal to 1, we have 1 equal to the magnitude of 1 plus epsilon. 1 to the infinity is therefore written as follows. Using binomial expansion, this can be expanded as follows. When we simplify, we get this. Epsilon times infinity is equal to 1. We ignore any term that has only epsilon because it is too small, as well as the terms represented by the dots. This gives 1 plus 1 plus 1/2 plus 1/6, and this is approximately equal to 2.7. We have arrived at the same result, so there is nothing special about 1. I am sure your head is hurting right now, so let's leave it here for today. We shall continue with the development in subsequent videos, so subscribe so that you don't miss any update. See you next time on the Classical Universe.